Hello, Advanced Physics class. This is Dr. Brinzy here, and this is a continuation of lesson 6.6. And in class, what we learned is that when you have forces on a roller coaster, you can approximate, or actually you can consider some of those as circular motion. So some parts of the roller coaster here up at the top can be considered circular motion. And so what we can do is we can say that when we're on this part of the track or on this part of the track, we can think of that part of the track as part of a circle, and then we can apply the formulas for uniform circular motion to those parts of the track. And so right here over on the left, when we are at the top of the roller coaster, what we learned is that normal force is pointing up, gravitational force is pointing down, but what we also learned is that since we have a centripetal acceleration pointing downward, then we know that normal force has to be less than gravitational force right here. Okay, I don't know if you guys can see my cursor moving around. I'm using some software I haven't used before or in a long time. On the other hand, when we're at the bottom of the curve or at the bottom of a circle, we have very similar situation with forces. We have normal force and we have gravitational force. But in this case, since centripetal acceleration is pointing up toward the center of the circle rather than down toward the center of the circle, we now have a case where normal force is greater than gravitational force. And so when you're at the bottom of a circle on a roller coaster, you feel heavier because you're feeling more normal force being applied to your posterior. And when you're on the top of the circle, you are experiencing a little bit of lightweight, feeling lighter than you usually do because you're not feeling as much normal force as you're used to. And so you kind of like have this feeling that you're falling. And in kind of some sense you are, since centripetal acceleration is pointing downward. Now, the other thing I want to point out to you is forces on the loop-the-loop. So a loop-the-loop goes something like this. So you come into the loop and then you make a big loop like that. And then you come out of the loop like that. So we can attribute a radius to this loop, radius r. Okay. Whoa, that's kind of looking funky, so let's change that. Try that again. So here's a radius r. Good. And then we are going to go around that loop with some tangential velocity or tangential speed v. And we can figure out that any time in this loop-the-loop, that the centripetal acceleration has to be equal to v squared over r. And likewise at the top of the loop, our centripetal acceleration has to equal v squared over r. But this time at the top, it's pointing in the opposite direction. Okay, so just like I did with the roller coaster, let's draw a free body diagram of this person at the bottom of the loop-the-loop. So something like that. And in this case, we're not going to have anything that's much different than what we had for the roller coaster. We're going to have normal force pointing upward. Sorry about that. Try that again. Normal force. Hold on a second here. Let me recalibrate my board here just a second. I'll be right back. Just pause the video here for a moment. Okay, I'm back. I've calibrated the board again, so let me try to actually draw this little end. There we go. All right, now it's not going crazy on me. So normal force is pointing up, gravity is pointing down, and when we're at the bottom of the loop, the centripetal force is going to be pointing up. So that means that we need to have normal force, a normal force that's greater than Fg. Okay. Now it's going to look a little different at the top of the loop. So at the top of the loop-to-loop, unlike the roller coaster, we are inside the loop this time. And so gravity is pointing down. But in this situation, if we're inside the loop, normal force is also pointing down. And this time what happens is that Fn and Fg, normal force and gravity, work together to provide our net force, okay, which is our centripetal force. So that's one big difference between a loop-the-loop and a roller coaster, is that normal force and gravity, there is a moment where they actually work together in tandem. Okay? Okay, with that, now that we understand the concept of how forces work in a loop-the-loop and how they work on a roller coaster, let's work on an example problem here. So, alright, so we have a loop-the-loop here, and we want to figure out what is the normal force on the car. So we have a car right here, and we want to figure out the normal force on that car when it reaches the top of the loop-the-loop up here. Okay, so what I want to do is I want to draw a free body diagram at the top. So let's, I'll just put it right here on the diagram. Well, actually, no, that's not going to work. I just don't have enough room. So let's draw the free body diagram of the car on the top of the loop over here. Okay, and I'm just going to use a single dot. So we have gravity always pointing down, and we also have normal force pointing downward. Since we are inside the loop. And finally, our centripetal acceleration is also pointing downward. So all of these things are pointing down. All right, so the next thing I want to do is I want to write out Newton's second law. F net equals mass times acceleration. And I want to add up all the forces and need to figure out what F net is. Well, Fg is going in the negative direction, and normal force is going in the negative direction. So actually both of those will have a negative sign. So that's F net. And then on the other side of the equation, I want to write mass times acceleration. Well, the acceleration of this car at the top of the loop is going to be centripetal acceleration, since we're inside of a circle. All right, well, I am being asked for normal force, so basically what is this Fn here? So that's what I want to solve for. Oh, one other thing, oops, I just saw something. I forgot to make this negative, because centripetal acceleration is negative, so let's change that right now. Whoop. Mass times centripetal acceleration. All right, so if I multiply both sides of this equation by -1, I'm going to get Fn plus Fg equals m times ac. And then what I can do is I can subtract Fg from both sides. So normal force equals m ac minus gravitational force. Well, that gravitational force is just m times g. The centripetal acceleration is v squared divided by r. So now I have an equation, and I think I know everything I need to know to plug in for this. Let's go ahead and first factor out the mass, since that is common in both terms. And then I just get that, v squared over r minus g Now let's go ahead and plug some things in. The mass of the car is 0.5 kilograms. V squared, it's saying at the top of the circle, it's going 5.5 meters per second. So I need to make sure that I square that. Ooh, this is starting to look ugly. Let me back that up. Let's try that again. 5.5 squared divided by the radius of the circle, which is 2.0 meters. And then I need to subtract 9.8 from that. Let's go back again one more time. Make that a little bit neater. 9.8. Okay. All right, so once I evaluate that, I should be able to get the value for my normal force. And I am going to do a bunch of mental math right now since I did not bring my calculator with me. Well, I suppose I could punch it into my computer, but let's see here. Now 5.5 squared, that is going to be a number between 5 squared, which is 25, and 6 squared, which is 36. So take something a little bit larger than a halfway point. So let's say 31. I take 31 divided by 2, I get 15.5. So now I have 0.5 times 15.5, and you can double check to see if I got that right on your own calculator. I'm just like going off the top of my head right now. So 15.5 minus 9.8, that is a number that's going to be close to 5.5. Just a little bit more. Let's say we'll call it 5.7. But then I have to take that 5.7. So this is 5.7. Okay. Now, if I say that 5.7 looks a lot like 5.6 because I'm doing mental math, and if I take 56 divided by 2, I get 25, 26, 27, 28. 28. So, 28 newtons, somewhere around there. You can probably correct me on yourself and probably get a bit more accurate number than I do. But anyway, there's the mental math. And that is how you can find the amount of normal force that's needed at the top of the loop here. All right, so go ahead and work on the lesson 6.6 practice. Those are due tomorrow. And if you have any questions, feel free to stop in early tomorrow morning and I'll do my best to help you out. All right, see you tomorrow. Bye.